So next we have Bob Watson talking online. He's from Jodrell Bank Centre for Astrophysics at University of Manchester. He's going to talk about Starlink in your backyard, a DIY approach to satellite monitoring and data analysis. If Bob is there.
I am here. Let me just sort out my screen. Oops, not.
We hear you.
Right, it's highlighting the wrong screen. Right, that's the one. And if I start. Okay. So as Mike's saying, yes, I'm from Jodrell Bank. This is a bit of a side project since my main job is working on SKA Regional Centre development.
Sorry, Bob, we can't see your slides.
You can't? Oh.
No, sorry.
Okay. It's highlighting screen 2. All right, let's. Again. Five. Which screen? Right. What are you seeing?
We see your slides, not quite full screen. Oh, no, they are full screen.
Right, okay. Go. Right, oh, that's what I thought did last time. Okay, right. So I'm going to talk about a side project, which was started from sort of doing tests at Jodrell. So like Mike mentioned in his first talk this morning, if you look at the sky about 10 years ago, you would have seen at 10 gigahertz this string of Pearl, which are sort of TV satellites, which are in the geosynchronous orbits. But now, 10 years later, this was done with the Quixote experiment, which is just about to start operations again at 10 gigahertz. We now have these Starlink satellites on OneWeb, which are no longer restricted to that arc in the sky, are now everywhere, and are sort of brighter than the sun when you're observing in that particular wave band. So at Jodrell, we started trying to do some monitoring with the Mark II telescope, and so you want to do this monitoring in order just to, as has been mentioned before, make sure that the satellite companies are complying with international and national regulations. So the spectrum management, you want to make sure that they're restricted to their particular bands. And there's one astronomical band, which is at 10.6 to 10.7 gigahertz, which is right on the low end, which is very small. Unfortunately, the universe doesn't know about licensing agreements, and so just transmits everywhere. And radio astronomy, being a passive observing thing, can generally try, in the past, could look with sort of gigahertz bandwidths, but now we're being restricted. And this the Starlink and OneWeb will wipe out two gigs in a rather interesting band, which is a band I started working in about 40 years ago with the CMB experiment with in Tenerife. So I'm saying we tried to do some monitoring with the Mark II, which has about a 1/10 of a degree beam. And as you can see here, we've got these sort of satellites going from west to east. So we could see close misses. I think so. Federico pointed out they had a similar experience where you see close misses. So you can see that the noise level is still subjective to stuff coming in through the side lobes. If you go to a small TV satellite dish that's got about a 4-degree beam, you can expect to see a pass every couple of minutes. But then there's these half-pipe bent plate type experiments, mainly aimed at sort of looking at the early universe, which are very large, lower frequency. But if you go to 10 gigahertz, it's also easier to make a bent plate in the form of a parabola. And then you get a 40-degree beam in one axis and four degrees in the other. And then you pick up a satellite about every 30 seconds, which is sort of ideal if you want to do monitoring. So the idea, so I sort of started this sort of open science type project whereby we have, you can buy just about everything off the shelf and produce it yourself and set the data out into the public. And so anybody could sort of do this with a moderate outlay of money. So you need a standard. So I'm using a Sky wideband, which has a slight inconvenience in that the LO I think is set to 10.7 gigahertz. So you just miss the first part of the first band. But I've just modified mine since I do interferometry so I can change each LO and use the same LO on different ones. So I can pull that down in the future. I originally had produced a sort of ad hoc DIY kitchen table type project using foam card and a bit of bent plastic with some kitchen foil on it, which worked remarkably well. Unfortunately, the Manchester weather got the better of it, so that died around about Christmas last year. So I came up with the idea of a 3D printed antenna, which would be much more robust and much more repeatable. Also, for the actual receivers, they have these software-defined radio, which is basically redeveloped dongles that we use to pick up direct digital TV, but they can be repurposed, and there's now specialized things which will have more broader bandwidth. And you can actually just use a Raspberry Pi computer to log the data, and that can just run 24 hours a day. And you can use Python to actually do some of the online processing, produce plots every 10 minutes, and store that all to a relatively cheap SSD, which you can plug in and get data transferred over the internet. So I've produced one through several iterations. So the idea is you can print this out on a small 3D printer with a sort of 22 by 22 centimeter plate, which is what I've got, which is why. And I've also bundled up all the instructions on how to do this and put it on the Instructables website. So people, schools, interested hobbyists can have a go at this, and it might be a good one for a future hackathon. So the SDRs are, so I'm saying, relatively cheap, going from about sort of 10 euros up to, for a really cheap one, to sort of 20, 40 for a better one. To get the broader bandwidth and the being able to scan over large multi-gigahertz data, the 2 gigahertz at the downlink, you can have to splash out a bit more for like 300 euros for a Hack RF1. And I've just started experimenting with interferometry, in which case you can get this, slightly old now, Kyberush, and a Kraken is out, which can basically got 4 of these dongles all synced up together, so you can actually do that takes data simultaneously and get direction finding. I'll come on to that a bit later. So the monitoring software. So if you click, you can see there's a link. So you can actually, I've made a little hole in my firewall, so you can actually get images of my 10-minute plots, and I'll leave that open during the conference. So the Raspberry Pi, you can have a full-blown Linux distribution on it. So I'm using Ubuntu server, since I don't really need the desktop. And you have the SDR software has command line commands for just scanning a set part of the spectrum, and then you could dump it out onto a pipe, and then you can have Python teams to pick that up, process it, and dump in hourly chunks, and also reduce the plots. So you can have a cron tab, which is a set of commands on a sequence at particular times of day. So just before midnight, pull down the TLE from Celestrak for the day, and that's stored along with the data. And that calculates the expected transits for the next hour. So I can do these plots. So I better explain this plot. So This is the downlink bands. So this is what's known as a waterfall plot. So time's actually going upwards. So you can see the 8 bands. Unfortunately, the first one's cut off slightly. And this is these are also checkable things. It tends to be one web, and that does seem to occupy the lowest band. And these are the beacons. So you see the Doppler. So this is a 2 gigahertz band here, and this one is just a 1 megahertz band. And so you can see the Doppler shift of the satellite, and also where there's a data transmission at the same frequency, then you get this all fuzz across there. And I've collected together all the my scripts and put that on GitHub. And so the scripts are there, though there's not much instructions on how to install it yet. So that's what I'm working on. So just saying, this is probably going a bit too much detail, but it sort of points out what the data is being collected and how it works. So you've got this command taking 2 gigahertz of data, a certain resolution, and just dumps it into this Python file, processes it. But then that gets chunked up into sort of into 5 megahertz chunks 4 times a second. So that's quite a good rate. And then the more standard 1 megahertz SDR dongle monitors this beacon band, and you get a 1 kilohertz resolution, so that covers 1024 frequency bins, and that's all downloaded. And so the data.
Bob, just to say 4 minutes.
Okay, right. I think that's about what I'm expecting. So the data is stored and on SD disk, and I've just bundled together about a month's worth of data and dumped that on Zenodo, so you can have another play with that if anybody's brave enough to try it during the hackathon. One thing I did do with the data, so I did try to sort of get an absolute calibration using the sun. That didn't work too well, but I realized you can use one web, which comes over north-south, south-north, and do a median filtering. So these are plots of data from a square law detector. So all these little specks you can see are actually Starlink crossings, but if you use a median filter, you can actually pull out the beam, so you can actually see this elongated beam, not quite in the zenith, so something's slightly off. So it's probably just the focus is slightly off, or what it's sitting on isn't very flat. Jodrell, we're building a bigger system, so this will go in the control room, and it's sort of going in tests at the moment. Twice as big, so it'll have a narrow beam, but more signal, and we'd like to plug it into the experimental software correlator under development at Jodrell, in which case you can start exploring the delay space and really tie this down. And if we put something similar out at each of the stations, we could actually measure these satellites to sort of kilometer resolution orbits. I think Simon Garrington's got some software for doing that. So I'll just quickly finish on the idea of interferometry. So we've got this long beam, but we'd like to know where the satellite crosses in that beam, so you can interfere the LNB data, and that can tell you where in the beam it crosses. That helps tie down the orbit a bit better as well. So this just a quick summary. So you can depending on how much you want to get into this, you can make something for about less than €500. Data, in terms of SKA, is tiny, but so 1 terabyte is data, and so I've got more data than I know what to do with. So that's why I put it out into the public. Probably need sort of AI to sort of go through and characterize these transits. Some of the transits are quite interesting, that you can actually see while it's going through, the beam changes, so you get a Gaussian and a step. So that might become useful for sort of things that Federico was mentioning, to try and figure out how the algorithm for doing the pointing of the satellite. and we can sort of integrate down these bands and see if there are any leakage out into other bands. And it's probably just overall a very good outreach problem where sort of people in the street can sort of do this and see the problem for themselves. So see this sort of every 30 seconds as a burst of 10 gigahertz signal. But if you're not actually using it for your internet, it just gets in the way of radio astronomy. I think I'll stop there. So, any questions at this time?
That's perfect. Thanks very much, Bob. We have time for one question. If anyone has one? Okay, I can't spot any, so if you have any questions, please ask on Slack.